So we have now finished our very abstract ideas. We have finally gotten to Gauss's law, and you really might not have a feeling yet of why we actually want to do this. And basically, Gauss's law is relating the flux to the enclosed charge. And flux then is related to that surface area of the electric field. And so really now we have three things that we can relate together. We have our flux, we have charge enclosed, and then we have electric field dot dA over our, that's supposed to be an integral sign, I've done a bad job, over our closed surface. So we can now relate these three things together because in particular, those are just the same. And depending on what you have, you might be given the electric field, and if you know its symmetry, notice that almost always when we're using the integral form, we have to know something about the symmetry. Basically, once you have one of these, you can find the other. So if we know something about what our electric field is doing, we can find the charge enclosed. If you know what the charge enclosed is, and you have the right symmetry, you can actually find the electric field. So that's the key. The key thing you're going to do with Gauss's law in many cases is calculate the electric field. And again, it's going to be simpler than Coulomb's law for many situations. But that only works if you know the symmetry of the charge distribution and choose a good Gaussian surface. And remember that your Gaussian surface needs to have a symmetry that relates to the electric field. And the reason you're going to know that is because the symmetry of the charge distribution has the same the charge distribution and the electric field have the same symmetry. So symmetry is again key here. So if you skipped that entire section, you are probably going to struggle. Lastly, there are going to be some conceptual shortcuts that we can take using Gauss's law that basically you can check your reasoning for things, because if reasoning through it conflicts with Gauss's law, you have a problem. And the big one here, which is contained in this chapter, is thinking about conductors. How do charges behave in conductors? How do electric fields behave in conductors and around conductors? So there's going to be some conceptual tricks here, conceptual shortcuts that really come from Gauss's law. So again, that section might not make a lot of sense if you don't have a feeling yet for Gauss's law when you get to that. So let's just look at some quick little practices. And this isn't going to be the most meaningful application of Gauss's law, but my hope is it will give you something a little more tangible. So let's simply compare the flux, right? So remember that flux is going to be, and I'm just writing down Gauss's law for you, the integral over your closed surface of your electric field dot your dA. Now, if you think about that and you go, okay, I can kind of probably figure out how to do this surface integral over here in the circular case, but crap, that's going to be a nightmare to do for the square because some parts of the square are further away, so it doesn't actually have the right symmetry. But that's why Gauss's law has that last bit, Q enclosed over epsilon naught. So what is Q enclosed here? Well, that's just Q. In the square case, Q enclosed is the same Q. So phi of A equals phi of B. So again, this isn't that meaningful, but the point being is if all you need to do is calculate flux, look at how much charge is on the inside. You don't actually need to do that. You can usually skip that step. Again, if I asked you to find something about the electric field, for instance, maybe I said, hey, what's the average electric field on that surface, you know, in a certain type of average way? Well, then maybe you would want to use that. Again, the surface integral for this would be kind of unpleasant, but there will be some situations where we do go back and actually use this or try to use it in some simplified way. So here the question, hey, how does the flux compare? Trivial question because the charge enclosed is the same, so the flux is equal. Okay, what about now? So now again we look at this and go, okay, well, I know that my flux is in this situation, right? My electric field is radial, and so this is one of those nice cases where my flux, electric flux, is going to be E times A, where that's the surface area of my sphere, right? So we have this nice simplification. And now on the one hand, I see that this sphere is closer, right? So in this case, it's closer, which means I have a bigger electric field, and I have a smaller area. In this case, my sphere is bigger, but it's further away, so I have a smaller electric field. Well, okay, I don't know. Do they balance? Do they not? Again, the trick is, the shortcut, why we keep coming back to this, is that it's still equal to charge enclosed over epsilon naught. Charge enclosed is the same, so in this case, these two fluxes are the same. So again, it's true that in this case we have a bigger electric field in a smaller area. Here we have a smaller electric field in a bigger area. You can't always just know that, oh, those are definitely the same. Mathematically, in this case, you can do out the integral. Again, the sphere around a point charge we did do back in the first part, the first video for this section. But again, just from charge enclosed, we know they're equal. So please, please, please recognize that in many cases, if you need to know flux, just use charged enclosed. And again, in the next section, we will actually start using this to calculate properties of our electric field.